Welcome to today's session on active learning. In the previous sessions we looked at labels. We defined them, we saw why they varied, and discussed reasons why this variation might be meaningful. And naturally, when we talk about labels, there is also the question how do we acquire them, or what is a reasonable order in which to label the labels or annotate the labels to get a good machine learning algorithm with as little annotation costs as possible. And one procedure that was introduced to do so is so-called active learning. Labels are often the expensive part. Maybe we have abundant unlabeled data. For example, if we're in a hospital, maybe there are many examples somewhere on paper, but we really need to scan them or get a doctor to actually write down whatever they see on an X-ray image, for example, in a digital way. Maybe we could, in theory, do tons of experiments or laboratory tests, but we don't have the time to do so, or we don't know where to start. Sometimes labels require careful reading or inspection. Maybe we need an expert to give us information or to label the data, or we need to access to sensitive information. All that leads to the result that labeling can be very expensive, both money-wise and also time-wise. And then if the question is, if we can only label 100 cases, which 100 should we choose? And active learning is exactly answering this question. Active learning, where is it here, is a process in which a model or a selection rule chooses from this unlabeled pool the next examples that should be labeled. Then it gives it to the so-called oracle, which might be a person or an expert panel, a measurement, an experiment, and this oracle gives you the label. And the goal is then to reach the useful performance with fewer labels. Specifically, the active learning loop, since it's basically continuously labeling new data, retraining models, and so on, looks like that. We start with a small labeled data set. So, for example, in the beginning, we just randomly select some samples and annotate those. With those samples, we train our machine learning model. We use this machine learning model to predict the labels of the unlabeled data pool. Then, depending on the predictions that we get, the active learning model then chooses the most informative samples and tells us which are the ones that we should label next, gives them to the oracle for annotation, they provide the labels, and with the new labeled data set, we can then retrain our model. And basically you can repeat this circle and cycle until your annotation budget is exhausted, or further labels add no value to your prediction model. Okay, next we're going to look at which kind of selection strategies or so-called acquisition functions exist. There exists, for example, uncertainty sampling, which basically consider the uncertainty that we have in our predictions and chooses them for different reasons. For example, the ones with the smallest margin. So for example, here in this example, we see that the top two classes are nearly tied. So we say we are not too certain which of those two classes is the correct one, and acquiring a new label for such an instance would improve the model, give new information. We can also choose the labels, what to label next based on highest entropy. Entropy is the measure we looked at Unit 1. For example, if we look at this example, this is the one that has the highest entropy of all the 3 bars that we see here, and we would label this example next. So maybe just to explain again what those bar plots represent here, those are the predicted probabilities for those 3 classes, blue, orange, and green, for some instances. And it can be anything you might think of, just a 3-way classification task. Another measure is least confidence, when the top predicted class has low probability. So for example here, the top class has only 39% of probability, and if we want to choose the least confident prediction to sample next, it would be this one. You can see there are different measures that consider uncertainty in our predictions. And it's up to the researcher to choose which one is the most appropriate, because all of them optimized for slightly different metrics. Another way to choose the next examples is query by committee, where you can train several plausible models, which could, for example, be neural networks with different initializations. And then we query those examples on which the predictions differ the most. Because this kind of disagreement between the models can reveal regions where the data that we currently have is not too certain, and we would need more information there to improve our predictions. So for example, for those 2 images, we have the different models predict different colors for whatever example that we have, and those would be the images in this example that should be labeled next to improve our models the most. There is a slight change to this method, which is called Bayesian active learning by disagreement, where we do not only consider the disagreement of the models, but also consider where models are highly confident, because the so-called BALD, Bayesian active learning by disagreement, specifically searches for data points where individual members are both confident and they disagree with each other. And the idea here is that since all the models are very confident about their own predictions, but they disagree with each other, it shows that there actually is not enough evidence in those examples to properly set the decision boundary. And we would need more information exactly there to resolve this disagreement. Specifically, it uses a measure based on entropy. Here it's called mutual information, which is just the difference between those 2 entropy-related measures. Here the first part, this one, is the entropy, H, or the Greek letter eta for entropy, of our prediction, given our data point X and the whole data set the models were trained on, capital D. And this part here describes the overall uncertainty, measured as entropy, of the model's prediction for a given data point. And this one is high when the models disagree. So we want to maximize the score, so the first part needs to be large, and the second part needs to be small. And the second part describes the average uncertainty of each individual model in the committee. So the average is represented here by the expected value over theta. Theta is a parameter vector, so for example, it could be our weights in the neural network. So the expectation over the models of the entropy, H or eta, of our prediction given the data point and all the models. And this average uncertainty should be low to maximize our BALD score, and it is low when our individual models are certain. Okay, so now I presented you different strategies how to choose your next data points to label. And however, as with all the methods that we consider, it's always a trade-off, because even though active learning can reduce the budget that you need, may it be time-wise or money-wise, the caveats are that active learning creates generally not an independent random sample of your population, because whatever you have labeled so far already influences what you will label next. You build up your data set in this iterative way, and that's why you don't have independent random samples anymore. As a result, class frequencies may be distorted. You can have more uncertain or unusual cases. Cases close to the decision boundary can be overrepresented. And therefore, ordinary accuracy estimates may be misleading, because if you're sampling a lot of very difficult cases, your overall accuracy might be lower than it actually is on an independent random sample of your population. That's why it is suggested to keep a separate representative validation and test set. So basically, in the very beginning, when you randomly sample and annotate your data, you randomly sample and annotate even more, and this random sample should be used as validation and test set, and you just improve the training based on this active learning pipeline. Also, another important thing is data usually outlives models. So basically, if you look at the past couple of years, especially with the increase of capabilities with large language models, oftentimes the algorithms and the models change very quickly. However, the data that you have and that you have collected usually outlives that. And therefore, it is always the question, what is your goal? What do you want to do? And might it be worth it to collect proper independent data, even though it's more expensive compared to the active learning pipeline? We're funded by the Deutsche Forschungsgemeinschaft and our copyright. Goodbye.